I'm Valerie Cross from Miami University, not in Miami, Florida, and in Oxford, not in England, but in Ohio in the United
Oh,
States.
I'm
And
sorry.
so I always have to make that clear, but I just recently moved to Tampa, Florida. So now I am in Florida. So
Oh, yeah.
I just recently retired after 25 years, but this is a research that I started when I was on a sabbatical at the University of South Florida in Tampa.
That's
So
great. Yep.
I've done a lot of research in fuzzy set theory, my dissertation, but when I did my sabbatical, I ventured into machine learning and was working with some researchers there. And they had a system where they were trying to identify cancer diagnosis in different data sets. And so they had a system that they had set up, and I wanted to explore the use of fuzzy set similarity measures. A fuzzy set is basically a crisp set is a fuzzy set where all the membership degrees are 0 and 1, but with a fuzzy set, you have a degree of membership between 0 and 1, including 0 and 1. So there's ways to measure how similar fuzzy sets are. So basically, we took their system and modified it. So I'll give a little introduction, a little bit about fuzzy similarity, fuzzy set similarity, the overall initial algorithm. The first part of this, I have to explain, we presented at the International Conference of Fuzzy Systems last year, which was supposed to be in Edinburgh, but again, it was all virtual. And then how we design experiments and results. And then for this conference, we extended it by looking at the feature grouping that we did and evaluating the feature subset to decide whether they were poor or better quality, and we included only the quality ones in our base classifiers. So basically, the problem with, and a lot of you are doing machine learning, and there's, one of the problems is there's huge numbers of features, but a few examples or samples for the data set. And this is especially true in biological applications. In our case, we had levels of gene expression for cancer patients, and we'd have, over 7,000 features and maybe less than 100 patients for the data. So we were trying to have accurate classification and eliminate a lot of the features. We used initially, in our initial experiment with which we continued, we used Relief F, which is a filter-based method to select the most promising features from this huge set of features. And we used an ensemble because ensembles are supposed to, in a way, give better predictive power. And the approach we used was a modification of random sample, modified random sample method. The difference is, instead of taking all the features that Relief F gives you and randomly picking from those features that the Relief F gives you, you group them into similar features and you create groups, and then you randomly pick features from those groups, because you want to reduce redundancy in the feature selection and have more variety in the features that you select. So the two questions, the first question that we did in our initial research is, can we use different grouping methods to group these expression levels into groups that were very similar and then randomly pick from those groups? And we did that and presented that work at the International Conference on Fuzzy Systems. And then in this, we wanted to say, okay, we're generating over 100 base classifiers in our ensemble, but how good are these base classifiers? Can we reduce the number of base classifiers that we're using and still get as good, if not better, different performance measures like accuracy, sensitivity, specificity, and the F measure? So that's what we were looking for. So this is our machine learning components. We put the features into Relief F. Relief F gives us a set of top rank features. We take a hierarchical clustering algorithm, and the measure of similarity is a fuzzy similarity measure. Before we do that clustering though, we put the gene level expressions into the 0-1 range, so they are in fuzzy set format. And so we get these different groups of feature subsets, and then we randomly select from each group a feature. So each ensemble will have the number of a number of features equal to the number of groups that we have created. And then we took a training classifier, just simple J48 classifier, and created our base classifiers and used majority voting method to decide whether this was a cancer diagnosis or not. The thing that you see in green is what we did to extend this work. We used feature subset evaluators. So instead of having always 101, we thought maybe we could get better feature subsets by evaluating them. And we'll talk about the different evaluators we use. And then, and so that's the additional part that we did. So we normalized the data, and how we normalized it, we took the original data and just simply used the value minus the minimum value for that feature, normalized by the difference in the maximum and minimum. And we did that test data separate from the actual the data that we used for recording whether it was a cancer diagnosis or not. So so we clamped the data so it would only be in the range from 0 to 1, but and it worked fine for the training set, but the test sample, since we didn't use it when we were in the training set, we may have had to clamp some of the values on the test data. So here's all the different similarity measures and relatedness measures that we used. The concordance correlation coefficient was originally used in some research at the University of South Florida. That's the only similarity or relatedness measure they use for grouping. But we added 6 more measures: the cosine similarity measure, Zada's measure, and T in that case is an aggregation function, a T norm, and typically it's min. Then the Jacquard index is a very famous from taxonomy back in the early 1917s, just the ratio of the intersection of the two sets over the union of the two sets. And last but not least, we used an inclusion measure, an aggregation of how much of set A is included in B and how much of set B is included in A. And the aggregation operator that we used 3, average, min, or max. Here is the overall original algorithm that we had. It used leave one out for developing the training set and the test data. And the parameters we had were N is the number of relief features that we selected. G was the number of groups that we created. S was the similarity measure, and E was the number of base classifiers. And we ranged these values for each of these values, and I'll go into a little more detail. But the important steps were normalizing the training data, using Relief F to get our top features, then using the similarity measure that was for the experiment to cluster them to groups, and building the E-base classifiers and adding them to the ensemble, and then applying the ensemble to the training data, the test data, and then recording whether it was, what kind of error it had or if it was successful, if it was a true positive, true negative, false positive, false negative. So these are the performance measures that we used. We had sensitivity, specificity, accuracy, and the F measure. So sensitivity, you probably all know this, it's just how many of the positive ones did you actually identify as positive. And specificity is how many negative, of the true negative ones did you actually identify. And accuracy is how many correct did you get, both positive and negative. Precision is worried about how many positives did you get, did you say were positive over the true positive cases. And F measure is a combination of precision and recall, and it ignores the basically ignores the false the false negatives. So it's not so it's doesn't is worried about that. So we used hierarchical clustering to create the groups, and there's different ways that you could determine the distance on creating your groups. We used the complete linkage approach, where we took the distance between two clusters as the farthest pair of vectors, and we would basically use that to how to merge the clusters. And the stopping criteria was we had ran through different sets of parameter values for G. And in the initial experiment, we were trying to find what combinations of these parameters, where would we get the highest values for each of these ensemble performance measures. These are the data sets that we use, the breast and the CNS, colon, and leukemia. The CNS is a neural system cancer. And the examples were the patients. And you can see the ratio between the number of features to the number of samples. None of these samples were over 100, examples that we had, but all of the 3 of them were over 7,000 features, and colon only had 2,000. So we ran the experiment. Let me see. We ran the experiments with different values for the N, G, and the different parameters. And for each data set, we recorded the highest value for each of these performance measures. Here's the recall or sensitivity. So we can see that basically for the leukemia data, it seemed like all the similarity measures and grouping did quite well in predicting, the true positives. But for CNS data set, it was the lowest. It had a very difficult time predicting, doing the true positive cases. So the measures, the cosine measure, which is the orange, seemed to perform the best in all the data sets except the leukemia, where it was the lowest. And inclusion min seemed to be the lowest or tied for the lowest for leukemia. And we did that for specificity. It's interesting that for all the data sets, for the most part, except for the breast data, all of them were over 0.9 for identifying the negative cases of cancer. The breast was the lowest, and interestingly enough, CNS, who had the worst sensitivity, seemed to have the best identification of true negatives. So, and we did this for also accuracy, and we also did it for the F measure. So the conclusions were that fuzzy set similarities performed as well as the initial concordance, or better than the initial concordance correlation coefficient that they had originally used in South Florida's research. But there wasn't a single fuzzy set measure that was best overall. It varied depending on the data set, and it varied depending on what performance measure for the ensemble you were using. Cosine seemed to have overall the performance measure for the breast, and it had the highest sensitivity or tied for the highest sensitivity for the colon data sets. The highest F measure was for the CNS data set, and the lowest was performance measures were for leukemia for cosine. And then Jacquard, the intersection over the union, had some good features. It was the highest for the data set, all data sets except for the breast data set, and it had the highest F measure for colon leukemia. And then inclusion min was tied for the highest specificity. So we looked at that and we summarized it. You know, really it's dependent on the particular data set and the performance measure. And a distinction exists across the data sets and performance measures. Cosine seemed to be the most consistent high performer over the data sets in many of the performance measures. And we would recommend that if a practitioner were wanting to increase the performance relative, he or she might a fuzzy similarity measure for grouping useful. And any of these feature subsets that were available, we just used all the feature subsets to create a over 100 base classifiers for the ensemble. So the next thing we thought about was, could we combine different measures of subset evaluators with these similarity measures and see if there's combinations that help work that reduce the number of base classifiers and produce just as high or not better than the original only fuzzy set similarity groupings. So that's what our next experiment was with. We picked out 3 different feature subset evaluators: interclass distance, maximal information compression index, and the consistency rate. And all of these, the larger the value, the better the feature subset is, because you want to have a lot of distance between the different classes. You want your feature subset to distinguish between instances that are in different classes. And the maximal information compression index says you're trying to reduce X and Y features into one feature. And if you do that and it produces a lot of error, then they really aren't redundant features. So the higher the error, then that's telling you you can't reduce these X and Y features to one feature. And so you did that over all the pairs of features in your group, in your feature subset that you randomly created from your different groups. And if it had a high maximal information compression value, then that feature subset was a good feature subset. And consistency ratio is you look at patterns, and basically if you have pattern A and it's inconsistent, where half of them are positive and half of them are negative, then this is not a good grouping for a feature subset. So you want a consistency rate. You take the maximum number of positive or negative cases. So if you had 10 examples and 8 of them were positive and 2 of them were negative, that would be a better case than a feature subset that had 5 positive and 5 negative, for example. So those are the measures, and we wanted to compare the effects of these grouping features using the fuzzy similarity measures with evaluating the groups that they produced, and picked only high quality ones. Since we weren't worried about finding highest values, we were basically wanting to compare, does using a feature subset evaluator basically improve the ensemble measures, and how much does it reduce the number of classifiers that you have to put in your ensemble. So these are the values that we set for our experiments. And our quality evaluator was a simple one. We took the maximum evaluation and only took the top half of the feature subsets that were created of the features. So if it was greater than that quality level, then we included that feature subset. If it wasn't, we left it out. And I presented a table where you see the bolds using the different evaluators on the top row there, ICD, MIC, whether it produced just as well or better sensitivity value than the none column, which did not use any evaluators. And the bottom row, you see the number of wins, if it tied or did better than the none column, which wasn't using any quality check on the feature subsets. So, we did this for sensitivity, specificity, all the different measures that we were using. And I'm not going to present all the tables, but I wanted to give you an idea of how we measured success or judged whether using an evaluator was better or not than just simply grouping and not determining the quality of the subset. So basically, here's looking at subset evaluators, the feature subset evaluators. So we had the number of wins per column over all 7 fuzzy set similarity measures times the 4 performance measures. So the fuzzy consistency evaluator was consistently tied for the best with 25 out of 28 wins against the baseline that did not use a feature subset evaluator. The CNS, for that data set, the interclass distance did the best, or tied for the best for accuracy, sensitivity, and the F measure, but ICD did the worst for specificity. There was less variety between the evaluators. All of them seemed to have the same number of wins for each performance measure. It was difficult to distinguish between these feature subset evaluators. And in leukemia, the fuzzy consistency evaluators seemed to be consistently the best or tied for the best with respect to all the performance measures. Then we could look at the fuzzy set similarity measures for each of the data sets also. Am I running out of time? How am I doing? Anyway, for the different ones, it basically seemed like the inclusion max was the best fuzzy set similarity in combination with the different feature subset evaluators. And then we looked at the pairs with the highest values. So if you look at the table, the highest value we got for colon, for example, was 0.925 for sensitivity. But a lot of the combinations of fuzzy set similarity measures and feature subset evaluators produced that value for colon. And similarly, for specificity, you could look at leukemia, and the highest value that we produced was 0.96 for specificity, and that was for leukemia using 2 different feature of fuzzy set similarity measures, inclusion max and the concordance correlation coefficient, but it paired up well with all 3 of the different feature subset evaluators. And the column at the end is the number of base classifiers. So you can see that with inclusion max and using maximal information compression index, we only needed 34 base classifiers to produce this 0.96 specificity, which greatly reduces the training time. You do it on only 34 base classifiers instead of 100 that we did when we didn't do any evaluation of the feature subset. And over on the left is the, the winners based on how many rows that they had in the table for sensitivity and for specificity for each of the either the feature subset evaluators or the fuzzy set similarity measures. So in most cases, fuzzy set similarity paired with a feature subset evaluator outperform the baseline case, which only used fuzzy set similarity measures. And typically, on average or generally, you only have to train on half the base classifiers if you used a feature subset evaluator. In general, it seemed like the fuzzy consistency index is the better performing feature subset evaluator in combination with a fuzzy set similarity measure. And the winner of, or the best in general, was the inclusion maximum aggregation similarity measure for performing. And basically, some future work that we hope to address is there was a lot of imbalance in the data sets. So maybe generating some more test data and using different methods to group, like k-means or similarity thresholding. We took a simple hierarchical clustering approach, and definitely different data sets, because you could see how performance varied greatly across the different data sets. So why does grouping with a certain similarity measure cause poor performance in the neural data set versus very good performance in leukemia? So we'd like to investigate, more data sets and try to understand the relationship of this matching with fuzzy set similarity measures. Thank you. And does anybody have any questions?